to solve the differential equation with Frobenius method. So before we solve this question, I want us to test for the singularity. Let's check if it has a regular singular point or an irregular singular point. Let's check whether it's analytic or it is not analytic. So the first step you are going to do in order to test for the singularity is to divide by the coefficient of your y prime prime. So if I'm dividing with the coefficient of my y prime prime, I'm left with y prime prime plus 4y prime divided by 8x plus y divided by 8 is equals to 0. So from here, I would assume that my p of x, my capital P of x, is equals to the coefficient of my y prime. So let p of x be equal to the coefficient of my y prime. So if p of x is equal to the coefficient of my y prime, I'm left with 4 over 8x. And of course, 4 over 8x is something as 1 over 2x. Okay, that's for my p of x. Then let q of x equals the coefficient of my y. So from here, I know that the coefficient of my y is 1 all over 8x. 1 all over 8x. Okay. So looking at these two fractions, the p of x and the q of x, we know that p of x and the q of x is not analytic at x equals 0. Like when x is equals to 0, when you say x should be 0, the q of x and the p of x turns to infinity. So it means that p of x is equals to infinity and q of x is equals to infinity. So if you check from here that when you put 0 into this equation, you see that both p of x and q of x is equals to infinity. So what we have here, the next step you have to do is to consider our small letter p of x and our small letter q of x. So if we should do that, we know that our small letter p of x is equals to x minus x naught capital letter p of x. Okay, so as I explained earlier, the small letter p of x is to check whether this equation is regular or if it is irregular. So, and recall what I said, that the imputation of the x that you used here should be the value of your x naught in your p of x. So, since my imputation was x equals to 0, it means that I am left with x minus 0 multiplied by p of x. And of course, p of x is equals to 1 over 2x. So, times 1 over 2x. So, I'm left with, I know that I have x, of course, x minus 0 is x, times 1 over 2x. So, this is my p of x, times 1 over 2x. So, these can cancel this, I'm left with 1 over 2. So let's check for the small q of x. So the small q of x, of course, is equals to x minus x naught squared q of x. Okay, so we know that our x naught is equals to 0. So we are left with x minus 0 raised to the power of 2. And of course, q of x is 1 over 8x. So I have times 1 over 8x. So x minus 0 is x squared times 1 over 8x. So if it cancels, I'm left with x all over 8. From here, from these two from these two fractions, we see that P of x and Q of x is analytic. Okay, is analytic. That means, what I mean by is analytic is that it is not equals to infinity. It is not equals to infinity. There is no value of x that you put in this Q of x that will give infinity. And of course, there is no value of x here. So two of them are analytic, and it has a regular singular point. And it has a regular singular point about the origin. Okay, as you can see, as I explained earlier, a regular point can be determined if the small letter p of x and the small letter q of x is not equal to infinity. So if it's not equal to infinity, it is a regular point. But if it is equal to infinity, let's assume that after cancelling, maybe I have x here. So from here, I will know that, of course, I will have an infinity if I impute 0 into this equation. But since there's no x on the denominator, I will not have infinity. And of course, in this equation as well, I can't have infinity here. So when you have a particular solution, an answer that is not equal to infinity, it is a regular point, a regular singular point. But if it is equal to infinity, it's an irregular singular point. So, and it's about the origin. The reason why I say it's about the origin, of course, is we know that from here, x is equals to 0. So since x started from 0, is from the origin. So from what we've done here, it shows that the equation we are going to solve is analytic. It is the P of x and the Q of x that determines whether it's analytic or not. So the P of x and the Q of x from our explanation shows that this equation is analytic and it can be solvable. So let's solve the differential equation itself. So I'll have to erase here. Using Fobrenius method of solving differential equation, I know that my y is equals to the summation of from n equals 0 to infinity a subscript n x raised to the power n plus c. So this is the series for Fobrenius. Then our y prime is equals to the summation of from n equals 0 to infinity. Of course, this power will multiply the whole the base. So I'm left with n plus c a subscript n x raised to the power of. So I'm to subtract 1 from the power. So I have n plus c minus 1. So the last but not the least is my y prime. My y prime is equals to the summation of from n equals 0 to infinity. Of course, this power will still multiply everything. So my y prime was derived from this, while my the second differential will be derived from here. So the power here is multiplying everything. So I'm left with n plus c minus 1, n plus c, and a subscript n x raised to the power of n plus c. We have to subtract 1 from here as well. So minus 1 will give me minus 2. So I'm to use the values of my y and my y prime, and of course my y prime to substitute into this equation. So I'm left with if I substitute, I have that my 8x multiplied by y prime, and of course my y prime is equal to some function, summation of from n equals 0 to infinity, n plus c minus 1, n plus c, a subscript n, x to the power of n plus c minus 2. So this is mine for the first one. Then for the second one,
For the first one.
so this is for the first one. Then for the second one, I have 4y. So 4y, I have 4, of course my y prime is equal to some function, this. So I have summation of from n equals 0 to infinity, n plus c, a subscript n, x to the power n plus c minus 1. And for the last, which is just y, of course this is my y, plus the summation of from n equals 0 to infinity, a subscript n, x to the power of n plus c. All these are equals to 0. So, using my law of indices, of course, I can, from here, you know that x is raised to the power of 1. And of course, from here, I know that x is raised to the power of n plus c minus 2. So, using the law of indices on my x, I know that my x should be x raised to the power of n plus c minus 2. With the law of indices, I'm to add my powers, okay? Since they are multiplication laws, and of course their bases are the same. So I'll add their powers. So n plus c minus 2 plus 1. So I have x to the power of n plus c minus 1. So here I have 8 summation of from n equals 0 to infinity. Okay, so n plus c minus 1, and of course n plus c, close brackets, a subscript n, x to the power of n plus c minus 1, because from here. So plus 4 summation of from n equals 0 to infinity. I'm bringing everything down. So I have n plus c, a subscript n, x to the power of n plus c minus 1. And for the last, plus the summation of n equals 0 to infinity, a subscript n, x to the power n plus c. All these are equal to 0. So the next step is to arrange all the powers of x to be the same. So I need to make all the powers of my x to be the same. So the question pops up, how should I, or what method can I use to make all the values of the powers of x to be the same, the powers of x? So if in the first equation, if I should let n minus 1 equals k, let's say from the first equation, from the first summation, first and second summation, they are the same. From the first and second summation, I would say let n minus 1 equals k. Okay, so assuming that it was 2 here, it would have been n minus 2 equals k. And of course, assuming it was negative 2, it would have been n minus 2 equals k. So since it's negative 1, n minus 1 equals k. So it's from here, I know that my n is equals to k plus 1. My n is equals to k plus 1. Okay, so wherever I see n, I indicate k plus 1. Okay, and wherever I see n minus 1, I should know that it's actually equal to k. So from here, I know that I have 8 summation of, but I know that my n is equals to 0. So if my n is equals to 0, if n is equals to 0, k is equals to minus 1 to infinity. Now let's go to this place. I have n minus 1. I know that my n minus 1 is k. So on this first bracket, I have k plus c. So I have k plus c. K plus c. And on the second one, I have n, which of course I know that my n is k plus 1. So if my n is k plus 1, I have k plus 1 plus c. So in this case, I have k plus 1 plus c. And on the a subscript n, of course, I know that my n is equal to k plus 1. So this changes to a k plus 1. X raised to the power of, I know that my n minus 1 is equals to k. Sorry, n minus 1 is equals to k, yes. So I have k plus c. So on the power, I have k plus c. Plus, I'm going to do the same thing for this one. Of course, I have four summation of from k equals -1, because the same approach. Just when n is equals to 0, what is the value of k? So k will be equals to -1 to infinity. And of course, I know that my n is equals to k plus 1. So I have k plus 1, of course, plus c. So here I have k plus 1 plus c. A subscript, I know that my n is equals to k plus 1. So I have k plus 1. And of course, I know that my n minus 1 is equals to k. So I have k plus c. X raised to the power of k plus c. So I'm done with the first two summations. Now on the third summation, I will just say on this summation, I'll just say let k or let n equals k. Since I've succeeded in translating all my n to k. Okay, so the reason why to let n equals k in this one is because my aim earlier on, as I said, is I want to make all the powers of x to be the same. I want to make all the powers of x to be the same. So if I should let n equals k, I have plus summation of from n equals, from k actually, from k equals 0 to infinity, a subscript k, x raised to the power of k plus c. All these are equal to 0. Now the next problem we have here is to make all the limits, all the lower limits of k to be the same. As you can see from here, the lower limit of k is -1, and 0. So let us increase the value of k that has a lower limit to the highest limit of k. So here the highest limit of k here is 0. So I'm to increase the -1 and the -1 to, of course, to 0. So how can I do that? What I will just do is, I would say, when k is equals to -1 on this equation, what do I have? So if k is equals to -1, I have 8. Of course, k is -1. So here I have -1 plus c. Okay? So of course, -1 plus c is same thing as saying c minus 1. Okay? Now in this other one, I say let k equals -1. The reason why I start with -1 is because of k is equals to -1 for the lower limit. That's why I'm using -1 as my first instance. So since k is -1 here, so -1 plus 1, I know that here comes 0. So I'm left with c. Then the next one is -1 plus 1. I know that I have a subscript 0. And of course, x raised to the power of c minus 1. Because from here, k is -1. So I have -1 plus c, which is something as c minus 1. So that's for my first one. So this is for when k is equals to -1. So if you can recall from our number line, after -1, I have 0. Okay, after 0, I have 1. So since instead of it to do for when k equals 0, recall that my target is to increase k to 0. So I wouldn't do for the limit of k. I will just bring down everything as plus 8, the whole summation of k not equals to -1 this time, but equal to 0 to the infinity, k plus 1 plus c, a subscript k plus 1, x raised to the power of k plus c. So I'm going to use the same approach on this one to increase it to 0. So what am I going to do is just to let k equals minus 1. So if k is equals to minus 1, I have plus 4. I have minus 1 plus 1. Of course, it turns 0. So I'm left with only c. So I have 4c. Of course, minus 1 plus 1 gives me 0. So I have a subscript 0, x raised to the power of c minus 1. And of course, I don't need to do anything on this one because my k is already the same. So I just have to bring it down. So since I've done for k equals negative 1, I will bring this down. So I'm left with plus 4 summation of k not equal to negative 1 this time, but equal to 0. This is for the negative 1, this is equal to 0. To infinity, k plus 1 plus c, a subscript k plus 1, x raised to the power of k plus c. So then, as I said earlier, so of course I have to bring this down. I have plus summation of k equals 0 to infinity, a subscript k, x raised to the power of k plus c, all is equals to 0. So our next step here is to compare the coefficients of our, so let's say compare the coefficients of x. So I'm going to compare the coefficients of all the x that I have here. So I have to compare them. So the coefficient of x on this first one, as you can see, x is raised to the power of c minus 1. And of course, I also have another one that x is raised to the power of c minus 1. So these are the coefficients. So by comparison of the coefficients, I have that the coefficient of this first one is 8c bracket c minus 1. And the coefficient of this one is, okay, a naught. And the coefficient of this one is plus 4c a naught is equals to 0. Recall that the equation is equals to 0. So all this should be equal to 0. This is for my first equation. And this equation is when x is raised to the power of c minus 1. Okay, this is the equation of x raised to the power of c minus 1. So the next one we have here is this one. Is when x is raised to the power of k plus c. So if x is raised to the power of k plus c, let's compare the coefficients. So when comparing the coefficients, I want you to just take what you have. You can leave the sum out of it. Just take what you have inside the summation. So from the first one, I have 8 bracket k plus c, a bracket k plus c, bracket k plus 1 plus c, a subscript k plus 1. Okay, this is for the first one. And for the second one, I have plus 4 bracket k plus 1 plus c, a k plus 1. And of course, the last one, I have plus a k, a subscript k. All these are equal to 0. So let's call this equation 2. This happens when x is raised to the power of k plus c. So this is for the coefficient of when x is raised to the power of k plus c. This when x is raised to the power of c negative 1. So from equation 1, from my first equation, from equation 1, I want you to know that from equation 1, I want you to know that a naught is not equal to 0. Just note that from here, that a naught can never be equal to 0. So since I have a naught here and a naught here, I can decide to factor out a naught. So if I factor out a naught, I have 8c open bracket c minus 1 plus 4c all multiplied by a naught is equals to 0. From here, I know that, recall what I said, that a naught is not equal to 0. So I have 8c bracket c minus 1 plus 4c is equals to 0. So this is what you have. From here, I can start to expand this bracket. If I expand the bracket, I have, of course, 8c squared minus 8c plus 4c is equals to 0. I have 8c squared minus 4c is equals to 0. From here, I can divide all through by 4. If I divide all through by 4, I have c squared, I have 2c squared minus c is equals to 0. So of course, I can factor out c. If I should factor out c from here, I have that c to the bracket 2c minus 1 is equals to 0. From here, I know that my first c is equals to 0. My first is equals to 0, and my second c is equals to, I have 2c minus 1 is equals to 0. Okay, normal factorization method of solving quadratic equation. This is a quadratic equation, so normal factorization method. So c is equals to 0 and 2c minus 1 is equals to 0, which means that c is equals to 1 over 2. Okay, my first, let me call it c1 is equals to 0, and of course c2 is equals to 1 over 2. Okay, so the next thing I'm going to do here is to utilize the value of my c into the equation that I have. So I know that I have some function here from my equation 2. From equation 2, I know that I have some stuff here. So what I have to do is that I will take over the smaller the smaller a. As you can see, a subscript k plus 1 is greater than k. So I'm going to take k over, and I will make the highest k the subject of the highest a rather the subject of the formula. So since a subscript k plus 1 is greater than a subscript k, I will take a subscript k over by making this one the subject of the formula. So by doing that, I have 8 bracket k plus c bracket k plus 1 plus c a subscript k plus 1 plus 4 bracket k plus 1 plus c a subscript k plus 1 is equals to negative a subscript k. So from here, I recall that I want to make a subscript k plus 1 the subject of my formula, and I know that a subscript k plus 1 is a similar term in two of them, so I can factor. If I factor out a subscript k plus 1, I'm left with, I have 8 bracket k plus c bracket k plus 1 plus c plus 4 bracket k plus 1 plus c all multiplied by a subscript k plus 1 is equals to minus a subscript k. So from here I can divide by the value, the coefficients of a subscript k plus 1. So by dividing by the coefficients, I have a subscript k plus 1 is equals to negative a subscript k divided by the value 8 bracket k plus c k plus 1 plus c plus 4 bracket k plus 1 plus c. Okay, so I can break the denominator further. I can break it further. So let's do something here. I have a subscript k plus 1 is equal to negative a subscript k divided by, I know that k plus 1 plus c, this one has k plus 1 plus c, and this one also has k plus 1 plus c. So I use factorization method. So if I use factorization method, I'm left with, of course, I have k plus 1 plus c in one factor, and I have 8 brackets. I have 8 bracket k plus c plus 4 in the second bracket. Okay, since 2 of them are like, I'll pick one, and of course I'll add what is outside of the bracket. So this is the value of a plus k plus 1. So this equation is valid for when k is greater than or equal to 1. When k is greater than or equal to 1. Okay, and this equation is called the recurrence relation. This is what we call the recurrence relation. Okay, from here we have the recurrence relation. So we can further break things down. We know that there are 2 values of c. Okay, there are 2 values of c when c is equal to 0 and when c is equal to 1 over 2. So I'm going to impute when c is equal to 0, and I'm going to have a different recurrence equation from when c is equal to 0. I'm going to have a different recurrence equation for when c is equal to 1 over 2. So by doing that, I have okay, let's solve for when c is equal to 0. So wherever I see c, I impute 0. Okay, so I have a subscript k plus 1 is equal to negative a subscript k divided by, of course, c is 0 here. So I have k plus 1, and of course in the next bracket, I know that c is equal to 0. I know that c is equal to, so I have 8k plus 4. So I have 8k plus 4. So this is for my first c. So let's create a recurrence relation for this. Since I said my k should be greater than 1, greater than or equal to 1. So let's substitute values of k that are greater or equal to 1. Let's start from 1. So if k is equals to 1, let's assume that my k is equals to 1 from the recurrence equation. The reason why I used k is greater than or equal to 1 is from here. Okay? So I have when k is equals to 1, of course I have a2, I have, okay, I can actually start from 0. I can start from 0. The equation is can still start from, you can start from 0. Greater than or equal to 0. You can start from 0. Okay? The equation can start from 0. So that I need to have my a naught. The equation can start from 0. So I have I indicated that k should be greater than or equal to 0 because of course I need the value of my a naught. I need the value of my a naught from here. And of course you can still use another description by saying the lowest value of c is 0. Okay, and the next value of c is greater than 0. So you can use that to analyze this concept, okay? So k should be greater than or equal to 1 because I need the value of my a naught. So if k is equal to 0, since k is greater than or equal to 0, so since k, let's assume that k is equal to 0. So if k is equal to 0, I have, here should be 0, I have a1 is equals to negative a0 divided by k is equal to 0. So here is 0 plus 1, that's 1. 8 times 0, that's 0 plus 4. So for all this gives you, that is for your a1. Now for your for when this is when k is equal to 0. So let's do for when k is equal to 1. Okay, I'm picking the value from here. When I say greater than or equal to 0, it means the value should not be less than 0. It should start from 0 and above. So when k is equal to 0, I've done that. When k is equal to 1, I have, of course, 1 plus 1. I have a2 is equals to minus a1 divided by, I know that my value of k should be 2 in this one. So that will be 2 plus 1. 2 plus 1, 8 times 1 plus 4. So 2 plus 1 is 3. I have 3 times 8 times 1, that's 8 plus 4, 12. So times 12, that is 36. Okay, so I have 36 here minus a1 over 36. So, and I know that my a1 is equals to some function. So I know that here is something as saying, I know, okay, let's break this down. This is something as saying minus 1 over 36 times a1. Okay, so I have minus 1 over 36 times a1 is minus a0 over 4. Minus a0 over 4. So of course the negative cancels out. I have a0 divided by 36 times 4. So 36 times 4. (144). So I have 1 over 144. Okay, so as I said earlier, just impute the value of your a1 into the here, and of course multiply, you have this. So this is when k is equal to 1. Let's do for one more. Let's do one more. So let's do for k equals 2. So if k is equals to 2, I have a3. a3 is equals to a2 minus a2 divided by, so if k is equals to 2, this is when k is equals to 2. So if k is equals to 2, that means I have 2 plus 1. Sorry, I said when k is equals to 1. Sorry, I have, when k is equals to 1, I have 1 plus that's 2. So I have 2 times 8 times 1, that is 8, plus 4, that is 12. So I have 2 times 12, which is 24. So I have minus a1 over 24. So this is something as saying minus 1 over 24 times a1. And of course, I know that my a1 is equals to a0 negative a0 over 4. So I have minus 1 over 24 times minus a0 over 4. So it cancels out. I have a0 over, so let's check the calculator, a0 over 96. Okay, then for this, when k is equals to 2, I have 2 plus 1, which is 3, times 8 times 2, that's 16. 16 plus 4, 20. So here is 8 times 2 plus 4, which is 20. Here is 2 plus 1, which is 3. So 3 times 20, that is 60. So I have minus A2 over 60. And of course, A2 is equals to A0 over 96. So I have A3 is equals to minus, this thing is sent to saying minus 1 over 60 times A2. And I have negative 1 over 60. And of course, A2 is A0 over 96. So that is A0 over 96. I have negative A0 divided by 60 times 96, which is 5,760. So I would like to start from here. You can check for subsequent ones. So this is for when C is equals to 0. So let's do for when C is equals to 1 over 2. So when C is equals to 1 over 2, when C is equals to 1 over 2, I will go back to my recurrence equation. So I have to create a different recurrence equation for when C is equals to 1 over 2. So of course, I have, from here, I have A subscript K plus 1 is equals to negative A subscript K divided by, I know that my C is equals to 1 over 2. So I have 1 over 2. I have K plus 1 over 2, which gives me, first bracket, K plus 3 over 2. That is for the first bracket. Then for the second bracket, I know that my C is equals to 1 over 2. So I have, in the second bracket, I have 8 brackets K plus 1 over 2 plus 4. Okay, so this is for the recurrence equation for when K is equals to 1 over, when C is equals to 1 over 2. I can try to break this down, but let's take it from here. Okay, let's break it down. So we have A subscript K plus 1 is equals to minus A subscript K divided by K plus 3 over 2. If I expand these brackets, I have 8K. 8 times 1 over 2 gives me 4, and 4 plus 4 gives me 8. So I have this. So this is the recurrence equation for when, as I said earlier, when C is equals to 1 over 2. So let's create the series, solutions for when C is equals to 1 over 2. So creating solutions for that, I have creating the solutions. I have let's say when K is equals to 1, when K is equals to 0. So if K is equals to 0 from here, I have A subscript 1 is equals to negative A0 divided by, I know that my K is equals to 1, is equals to 0. So I have 3 over 2. I have 3 over 2 times, I know that my K is equals to 0. Of course, this turns to 0. So 3 over 2 times 8. So 3 over 2 times 8 gives me 12. So I have 12 here. Now, I'm going to do for when K is equals to 1. So if K is equals to 1, I have A subscript 1 plus 1, which is 2, is equals to minus A1 divided by, I know that my K here is 1. So I have 1 plus 3 over 2, which is 5 over 2. I have 5 over 2 multiplied by, of course, I know that my K is equals to 1. 8 times 1, which is 8, plus 8, which is 16. So this is being multiplied by 16. So I have 5 over 2 times 16. So I have over 40. And I know that this is same thing as saying minus 1/40 times A1. And of course, I know that I have minus 1/40 times minus A0/12. So this gives me A0 divided by 40 times 12. So 40 times 12 gives me 480. So 480. So we stopped at k equals 2 here. So I'm going to stop at k equals 2 as well. So when k is equals to 2, if k is equals to 2, I have a subscript 2 plus 1, which is 3. A3 is equals to minus A2 divided by, let's go back. So when k is equals to 2, so I have 2 plus 3/2, which is 7/2. 7/2. And I have 8 times 2, which is 16. So 16 plus 8, which is 24. So this is being multiplied by 24. So 7/2 is being multiplied by 24. Okay? So 7/2 multiplied by 24 gives me 84. So this gives me 84. And of course, I know that this is something as saying minus 1/84 times A2. Okay, let's punch the calculator again to confirm. So this is 2 plus 3/2. 2. Okay, 7/2, of course. So 8 times 2, 16 plus 8, 24. Okay, 84. So and of course A2 is equals to minus 1/84 times A2 is equals to A0/480. So I have A0/480. So which gives me minus A0 divided by 84 times 480, which gives me 40,320. So it gives me 40,320. So the total solution becomes, since I have solutions for c equals 1/2 and c equals 0, we know that the general solution of our y should be y is equals to A0, using y is equals to summation of from n equals 0 to infinity a subscript n x raised to the power of n plus c, which is the Frobenius summation. This is the Frobenius summation. So if I should break down this Frobenius summation, I have A0, when n is equals to 0, what do I have? I have A0 x raised to the power of c, plus when n is equals to 1, I have A1 x raised to the power of, when n is 1, that is 1 plus c. When n is equals to 2, that is A2 x raised to the power of, when n is equals to 2, that is 2 plus c. And when n is equals to 3, that is A3 x raised to the power of 3 plus c. It continues this way. So this is the general series from Frobenius method. So, but since we have two solutions for the first c and the second c, since you have two solutions for it, the general solution of Fobrenius becomes y is equals to, let's call this y1 plus y2. Okay, let's call the first one y1 plus the second one y2. So okay, let me fix it here. Let's fix it somewhere here. Okay, for the y1, which is for when c is equals to 0, let y1 be c equals 0. So I have that my y1 is equals to, let's form the series. You form each series from here, either your y1 or your y2, depending on the value of your c. So when c is equals to, this is when I'm trying to form the series from when c is equals to 0. So my y1 becomes from here, when c is equals to 0, I have a naught, and x raised to the power of 0 is 1. So that is a naught plus a1 x. Now 1 plus 0 gives me 1. So plus a2 x raised to the power of, here is 0. Remember, I'm doing for when c is equals to 0. So I have squared, and of course, if you do it for the third one, you have a3x cubed. It continues that way. This is for when x, this is for when c is equals to 0. So that is for your first solution. Now, when c is equals to 1/2, let's call that our y2. So our y2, let's go back here again. We know that c is already equals to 1/2. So we know that from here, we know that c is equals to 1/2. That means we have a naught x raised to the power of 1/2 plus a1 x raised to the power of, that means 1 plus 1/2 gives you 3/2 plus a2 x raised to the power of 2 plus that, which gives you 5/2 plus, that is 2 plus 1/2 gives me 5/2, and okay, this is a3 gives me x raised to the power of 7/2. It continues that way. Okay, we are not done yet. We are not done. I want to fix it somewhere. So, but we know that from the first, when c is equals to 0, on that c equals 0, our y1 equals a0 plus, we have a1x, okay, and we know that a1 is equals to minus a0/4 from when c is equals to 0. So I have minus a0/4, and of course x, this is a1x, x plus a2 is equals to a0/96. a2 is equals to a0/96 plus a0/96 x squared, because I'm in my a2, so this is x squared. Then a3 plus a3 is equals to, a3 from here is equals to negative a0/5760. So that is minus a0/5760 x cubed. This series continues. This is the last solution from when c is equals to 0. Now when c is equals to 1/2, let's say it's y2. y2 is equals to, we know, let's go back to our y2. So our y2, we have a0 x raised to the power of 1/2. a0 x raised to the power of 1/2 plus a1 x raised to the power of 3/2. And we know that a1 from here is minus 1/12 from here. So we have, that is minus a0/12 x. Recall that x is raised to the power of 3/2. X is raised to the power of 3/2. So x raised to the power of 3/2 plus that's a1, a2. Okay, that's a0, a1. Okay, so I'm in my a2. So my a2 is I know that it's a1. Okay, my a2 is a0/480. a0/480 plus a0/480. Of course, x raised to the power of, that is for my a2. That's x raised to the power of 5/2. X raised to the power of 5/2 plus my A3, which is negative A naught over 40,320, that is minus A naught divided by 40,320 x raised to the power of 7 over 2. So this equation continues. Okay, recall that I said the general solution of y is equal to y1 plus y2. Hence, my solution becomes y, which is the general solution, is equals to, let me call it y of x, is equals to A naught minus A naught x over 4 plus A naught x squared over 96 minus A naught over 5760 x cubed continuous plus, since I've already used A naught here, let me decide to use B naught. It doesn't matter, okay? It doesn't matter. So let me just change B naught based on this. So if I should use B naught, I have B naught x raised to the power of 1 over 2 minus B naught x raised to the power of 3 over 2 over 12 plus B naught x raised to the power of 5 over 2 over 480 minus B naught x raised to the power of 7 over 2 over 4,320. This series continues. So this is the answer to the question. Recall, if you decide not to use B naught, you can still consider using A naught. It doesn't matter. Okay? So if you like, you can factor out A naught. Okay, let's just finish the work. So if we should factor out A naught from and B naught from here, so we have that y of x is equals to, factoring out A naught, I have that A naught into the brackets 1 minus x over 4 plus x squared over 96 plus, okay, minus x cubed over 5760 dot plus B naught into the bracket x squared x raised to the power 1 over 2 minus x raised to the power of 3 over 2 divided by 12 plus x raised to the power of 5 over 2 divided by 480 minus x raised to the power of 7 over 2 divided by 40,320. The series continues. This is the answer to the question. So I hope that you understood the whole procedure. Thank you.